Okay. Yeah, thank you very much for the invitation. I'm very happy to be able to talk to you and hear mostly from you, hopefully some comments and some feedback about the work that we have been doing in the context of hydrodynamics, in particular chiral hydrodynamics of plasma and strong magnetic fields. Well, what is that all about? The picture gives you a bit of a taste of a crisp morning where you walk past this lake and you see some sort of chiral phenomena going on. You see some directions that are singled out by the trees, right? The trees are up, down, singling out one particular direction, somehow making space anisotropic, if you will. And you also know there's more stuff going on under the surface of the lake there. So that is going to be my metaphorical entry point to holography. So what's going on under the surface there of that lake? We can use that. We can use this, what we call the holographic extra direction. We can use that in order to describe some of the fluid phenomena in chiral fluids and fermion fluids. And the talk will mostly focus on the effects, but of course also highlight the methods. So if you have any questions at any time, just let me know. I can be more precise or less precise. So I'll start with some hydrodynamic methods. I'll point out what methods we are using and what the framework is. Then hydrodynamic results that will mostly be comprised of Kubo formulae that relates transport coefficients to 2-point functions, and then we will see that there will be novel transport effects. We'll talk a little bit about we'll talk about the holographic model. And then we'll talk about flowing towards a quantum critical point, or the possibility of performing, like using this description of a fluid, chiral fluid near a quantum critical point in the model that we will be discussing. So that's the rough idea. So let me give you a sneak preview of the results that I find exciting. So on the left-hand side, you see a picture, a schematic picture of the forest that I was outlining. On the title slide, you have your magnetic fields, which create one magnetic field that creates an anisotropy. This will always be aligned with the third direction, X3 or Z, whatever you want to call it. Then you have chiral fermions. In this case, I chose left-handed fermions here, and they are forming a fluid. And it's charged in that sense that it is a collection of left-handed fermions, so it carries axial charge, left-handed charge, and it's going to be a relativistic state, relativistic treatment that we are going to work with here. So there will be 5 novel transport effects in this type of fluid. It will be 1 perpendicular magnetic vorticity susceptibility. That doesn't mean too much at the moment, but it is a susceptibility, as it says, to what we call a magnetic vorticity. Then there will be a shear-induced conductivity. So that is really what the name says. You shear the fluid in, let's say, the XY plane, and that shear causes a charge conductivity. And then there will be 2 expansion-induced conductivities. So those 2 expansion-induced conductivities you can think of as cousins of the bulk viscosity, if you will, but they are truly charge conducting. So I will explain more what that is. See, these are 5 novel effects, and arising just because we have a fluid which is treated in a strong magnetic field. I'll qualify what strong means, and we have a chiral anomaly because we are working with a chiral fluid.
Sorry, I have a question. What is the difference between shear-induced conductivity and piezoelectricity?
Well, maybe you can tell me that it's the same thing. So that would be exciting for me, because I was trying to see if these effects are known already. And I suspect that some of them are actually. So bear with me for a second, and like, well, we'll get there in a few slides. And then I'll ask you again if this is the same thing. So that would be amazing, right? So if you guys could tell me some of these effects are hopefully not all of them, have already been seen, then that would be great. So there's one non-dissipative effect that we find, and I find most exciting here, and that's the shear-induced Hall conductivity. So because I find it so exciting, I gave you a little preview here. So what happens there is a charge current in X direction. This is that shear-induced Hall conductivity, C10. I wanted to call it the Kaminski coefficient, but somehow my 5 collaborators didn't agree with that. So we'll still discuss that. But yeah, this is basically the term that you also see in any shear in standard shear terms, like when you have the shear viscosity, then this is the type of term that you see. So this is just a shear in the YZ plane. And in response to that, perpendicular to that, there's an X in the X direction, the conductivity, charge conductivity, and that's why we decided to call it Hall conductivity. So there are also two Hall viscosities and some modified Hall physics, which I hopefully get to chat a little bit about. And in general, there will be Kubo relations for over 20 transport coefficients, which I will not talk about all of this, but I will structure this for you. So just a reminder, what are Kubo relations? So for the shear viscosity, so the response of the fluid when you have a fluid surface, and you're asking the question, if this fluid surface is moving, how much does it drag the adjacent fluid surfaces? That's what we call shear viscosity, or also I like to think of it as transverse momentum conductivity. So that shear viscosity eta is equal to, or can be related to this 2-point function of the energy momentum tensor, and it's an off-diagonal component. It's the XY component, spatial component, 2-point function. And so that's in general what these Kubo relations are. So what I promise you here is these types of relations between a transport coefficient, the macroscopic transport coefficients of hydrodynamics on one hand, and 2-point functions on the other. So that's what we've derived. And then the whole idea of this is then in the end, we will once we've derived this hydrodynamically, we use holography, a holographic model, to explicitly calculate these transport coefficients from such 2-point functions to show that our construction, our description, or hydrodynamic description makes sense. And so this is what we will be doing. Here's another example of this expansion-induced conductivity, just to show you another different example of a Kubo relation. Okay. So this didn't have too much content. This was kind of another overview slide. So let me continue. Again, yeah, whenever you have comments, then please let me know, right? So let me give you two examples where I think this might be useful and interesting. So relativistic Weyl semimetals, so just Weyl semimetals, would be an interesting material to think of. So there you have a 3+1 dimensional material. It contains relativistic Weyl fermions. It has a chiral anomaly in that sense. So you have these points where the band structures touch, and your dispersion relation is relativistic approximately. And then another interesting aspect of these materials is that they also apparently have a quantum critical point. And so this is this might be interesting to to study in these materials and to study these effects that I'll be talking about in these materials.
May I ask a question?
Of course, please.
Maybe I a little bit late because I wanted to ask about the previous slide. You shown that there is 20 coefficients, transport coefficients, but eventually when you perform some measurement, you measure what? Electric conductivity, thermal conductivity, and probably that's it. So you have to be able somehow to transform the rest of the coefficients to some measurable quantities. Am I correct?
Well, first, thanks for the question. You're right that it's difficult to measure these. I think well, I have an idea of, especially for this particular. I'm working on a measurement proposal for this particular coefficient C10 to single that one out. The reason why I think that some of these can be measured is that these require a particular geometric setup. And maybe you give me a few more slides and then I can point to something.
Okay, thank you.
So, but yeah, so you're right. And right now it looks hopeless. Like there's all these new transport coefficients and there's only so much I can measure. Yeah, thank you for the question. I think I can address it in a few slides. Yeah, so that's one example is the Weyl semimetals. Just in the back of our minds, we can also say we can also think of, for example, other fluids such as the plasma that is generated in heavy ion collisions, for example. That would also be a quark-gluon-plasma fluid of chiral quarks, and so you could also think of that as a possible application for this description that we're about to construct. So let me first lay out my language for what I think hydrodynamics is. So the question in hydrodynamics is which are the relevant quantities in a system near equilibrium, and how can we predict their behavior? So that is a question that hydrodynamics can answer. So hydrodynamics is an effective description of systems at late times and at large distances. So at late times, conserved quantities is really the only quantities that survive, like currents, for example, conserved currents, and those conserved currents or charges, they survive because they're protected by symmetries. Everything else diffuses away, decays. So small gradients is what we require for hydrodynamics to be valid compared to large temperatures. So to quantify that, I can use this little reminder here that what we can do is we can think of any hydrodynamic fluctuations to be expanded in Fourier modes. So just to give you the idea, so every mode, every fluctuation can be expanded in such Fourier modes because you have translation invariance, let's say, in the system. If not, then one has to do something different. But here, this is just time translation invariance. So what happens then is if you have a time derivative acting on any of the fluctuations, you get down a minus I omega from the inner derivative here. And so this tells me that what does small gradients mean? Small gradients compared to the temperature means that this omega, this frequency, is small compared to the temperature. And the same exercise tells you small gradients in the spatial directions means that your wave vector has a small magnitude compared to the temperature. So that's the type of fluctuations that we consider in hydrodynamics. And in this particular setup, we also need to say what strong magnetic field means. So what I mean by strong magnetic field is that the magnetic field is on the order 1. So in terms of these gradients, so the gradient to the power 0, in other words. So that's what I mean by a strong magnetic field. You don't need any gradients for this magnetic field to be present. That's another way of saying it.
Sorry, I have another non-expert question. When you say large temperature, you really mean with respect to some kind of frequency, not with respect to overall energy scale of a material that you want to describe, yes?
That's a very good question. Yeah, so in realistic materials, I believe one has to be careful with all kinds of background noise that potentially is there, and you would probably want to make electron scattering your main process in a material if you think about using hydrodynamic approaches. So you would want to suppress all other transport phenomena as much as you could, I'm imagining, right? So this is as far as I could read the literature, that's what one would do. And so yes, I mean, then the overall energy scale of the system also matters, like phonons, for example, and so on. So that would create noise and would destroy possible measurements. But just for this effect, yeah, that's all I need. Just
but you want to work, for example, in the neighborhood of a Dirac cone, not the whole band structure. Yes, so then if you have a large temperature, you look on the whole band structure, and this is not what you are interested in.
Right.
Yes. Can I make a comment that maybe may answer Jacek? So yeah, I assume that you were asking this question like thinking on electronics, in electrons hydrodynamics. And the point is that electron hydrodynamics is a little bit different in the sense that the energy scale that would play the role of temperature is the Fermi energy. Because typically the Fermi energy in a metal is like is quite large. And the story is that the importance of temperature, or at least having an energy scale, a large energy scale to have a hydrodynamic description, is that that large energy scale allows you to organize the quantities in a gradient sense. That allows you to say, okay, the derivative of this quantity or second derivatives are smaller than small derivatives. And that's compared to the energy scale that is setting that is like relevant for the system. And in an electronic system, most likely will be just like the Fermi energy.
Hey, thanks.
Yeah, thank you, Fran, for clarifying that. I mean, if you want to go all theoretical and say, is this type of description still, and this limit still applicable in cases where, for example, the temperature is 0? And I would say, or I can tell you yes, because that scale that Fran was mentioning, which here is played by the temperature, can be played by, for example, the chemical potential in 0 temperature systems. So that has also been developed like to an extent, where you have 0 temperature and the characteristic scale is, for example, the chemical potential. Okay. So let me continue with just a pictorial description of what this looks like. So my fluid I describe now as a set of fluid cells which are adjacent to each other, and each cell is centered around a certain point, space-time point x. So this contains time and space coordinate, this x here. It's a 4 vector, and to each fluid cell, I assign a fixed temperature and a certain fluid velocity. So it has a certain temperature, and it wants to go into a certain direction. And the adjacent cells, the neighboring cells, don't necessarily have the same temperature and don't necessarily go in exactly the same direction. So that can create shear between these and temperature gradients between these fluid cells. And that's the type of description that we're using. So we've turned now the overall uniform description of a fluid which has a uniform temperature, let's say, into a description where you allow these gradients that we were talking about. And that allows us also time dependence and dynamics. So that's the view of hydrodynamics. Now let's introduce some fields and quantities to work with. So just a reminder of what that hydrodynamic limit is written up here. Then a checklist on what hydrodynamics is. It's a universal effective field theory. So that's how I will treat it. That's how it's constructed. As such, it is an expansion in gradients of fields. So I have to tell you what the fields are in hydrodynamics. It's a systematic construction, and it can be rooted to in part at least in a generating functional. So an approach that we're used to from either particle physics or even gravity, where you derive all quantities from either a generating functional or from an action principle. So to an extent, hydrodynamics can be derived in this way as well. Originally, it was constructed in a more phenomenological way. So Landau and Lifshitz are doing a good job in describing how that happened. So the ingredients of hydrodynamics are hydrodynamic fields, as I mentioned, constitutive equations, conservation equations, and then sources. And so how do we, like, what are these in particular? There's the temperature field, there's the charge density, and there's the fluid velocity. And what is a constitutive equation? It's really a one-point function of conserved quantities. So remember, the energy momentum tensor is one conserved quantity if energy and momentum are conserved in your system. And the current is another example. So here I chose to give you the example of a charged current, which is conserved. And here's an ideal hydrodynamic part, the charge just flowing with the fluid velocity u alpha. It's a four velocity. So this alpha runs over 4 indices. It's the time and then the 3 spatial indices. And then you have derivative corrections that include partial mu's. The conservation equations are derived from the symmetries of a system. So this is for example, the charge conservation equation. The current J alpha is the charge current. It's conserved. Its divergence vanishes, and you can write the conservation equation also for the energy momentum tensor. And this gives you, for example, the continuity equation if you just consider this leading ideal part, right? So then you get that the gradient acts on these two terms, or like the divergence acts on this term in this way, dtn plus nabla dot j. So the changing over time changing charge is given by the divergence of that current, the spatial divergence of the current. And that's just the continuity equation. So we recognize some familiar structures here, and as a last ingredient, we need sources, and these sources are the metric and the gauge field. So the way that we think of this is really like we think of the metric always. It's just there. We just think of it as something that's not dynamical. We think of it as something that is there, that describes the setting for us, the space-time. What we do now, according to Luttinger, is we allow this space-time, this metric, to be a little deformed. And then what we will do is we act as if we are working in this slightly distorted space-time, and then use this formalism where we vary quantities with respect to that metric, and in the end set the metric to a flat value. So this is a method of sources or of background fields that is also familiar from particle physics, where it's mostly done for gauge fields. And so may I? Yeah, of course.
Those liquids can be compressible.
So right now I'm thinking of incompressible fluids, but in principle they can be, yeah.
Okay, thank you.
Good. So let's go and apply this formalism, or just go through this construction that I mentioned. So we start with the hydrodynamic construction. Here's the first step: constitutive equations. We need to write down our charge currents, and let's say for we talked about this briefly, but let me just annotate this. So these currents that we were talking about, there's the energy momentum tensor T mu nu, which I need to write down, and then there's the, let's say, a charge current J mu. And we already saw that the charge current has a leading ideal part with the charge density times the fluid velocity, and this is just one of the terms. I need to add up all the terms that are vectors in this case here, Lorentz vectors, So one more term could be now containing a gradient. So I might invent some coefficient here, and that coefficient multiplies that gradient, let's say, of the temperature. So this is another term that I can write down aside from this leading term here. And so now I keep doing this. I write down everything that has one Lorentz index basically, and up here I write down everything that has two Lorentz indices. That's what this first step means. All the possible tensor structures, including these examples here, like vorticity, for example, and this divergence of the fluid velocity. And I write all of them down, so that, and assign to each of them such a transport coefficient or such an unknown coefficient. So that's a whole lot of terms, lots of unnecessary terms. And so some of them we get rid of by the use of conservation equations, like the one that I showed earlier. This is the continuity equation again for the charge n. But most of them we will get rid of and restrict by the use of this entropy current argument. So the idea is that in these fluid elements that we talked about, that basically you view them as or Landau proposed this. You view each fluid element as a little universe where the entropy should only stay the same or increase. So this is what's called the local second law. And this is the way to write this. This is the entropy current. So within such a fluid cell, we want that the entropy current to either increase or to remain the same. So this seems a little odd if you haven't seen it before, but the nice thing is if this disturbs you a little bit, then you can show that this can also be at least in the example that we calculated, can be entirely derived. You get exactly the same restrictions on these constitutive relations in a different way that is slightly more modern. I alluded to this before. You can use generating functionals and use field theory arguments such as Onsarger relations on the 2-point functions, analyticity of the 2-point functions, word identities, and that will create the same constitutive equations, the same form, and you will end up with the same number of transport coefficients that are independent in that treatment. So for our purposes here, what we first get out of this whole construction of this page here is the most general hydrodynamic 1-point functions for fluids that are subjected to a strong magnetic field and which have charges, chiral charges. And this to be published should be changed because we already published that. Sorry, I overlooked that. Okay, so this is the result or part of the result of this exercise. So I will get rid of these annotations. So this is part of the result. You see, it's a mess. So there's the what we would think of as the energy density term in the energy momentum tensor. Here's a pressure term. Here's a heat current. And well, this is together. It needs to be symmetrized because the energy momentum tensor is symmetric in the indices mu nu. And here's some sort of tensor contribution. And I wrote them out here for the equilibrium in which you have a strong magnetic field. There's a lot of effects here. And this is already the restricted version. So this is what we got. Like after this procedure and after using all the restrictions that we can use, already in equilibrium, the equilibrium state looks extremely complicated. Well, it's not so bad because all of this has structure. So let's look at this M2S2, this term here. It's think of M2 as a certain susceptibility. S2 is a certain tensor structure, which we will see again. So we just see that appears in the energy, or what we think of as the energy. So we'll see that again. And the good thing is about this whole thing that we can understand why this is so complicated, and we can structure these expressions and coefficients, because they came from breaking symmetries. So if I restore the symmetry, for example, that the magnetic field broke, then many of these will disappear. So the magnetic field created an anisotropy. It broke rotation invariance. That's for one thing, what it did. But more specifically, the chiral symmetry has been broken because we have a chiral anomaly in our system because of the left-handed particles. We have parity broken because of the axial chemical potential. We have time reversal and spatial rotation symmetry broken by the magnetic field that we introduced. And that leads to all these transport effects that we have here. So if you're familiar with this paper by Haldane, then this is like this example in 2+1 dimensions where time reversal can be broken without having a magnetic field and kind of having a Hall response without a magnetic field. So this is kind of the same idea, but in 3+1 dimensions, what's happening with the symmetry breaking and creating transport phenomena from that. Okay, so this is all horribly complicated. So let me try to structure this a little bit. So we start with hydrodynamic calculation of correlators. So what we want as the next step, we want hydrodynamic two-point functions. And again, this is, I should correct this. This is already published. The variation of the constitutive relations of these one-point functions that we just looked at in the previous page, that's what gives us these desired two-point functions that I mentioned. So as I said before, you can vary with respect to these sources, one of which is the gauge field. A alpha is the gauge potential from which you can calculate electric and magnetic field. And so this variation of the T mu nu energy momentum tensor with respect to this source for the charge current gives you a two-point function, the retarded Green's function. That's what this is supposed to mean, of T with the energy momentum tensor with the current. So if I write this slightly differently, it might be more useful, more recognizable. T mu nu J alpha. And this is the retarded Green's function of these two operators when I vary the constitutive equation of the energy momentum tensor with respect to the source, the gauge field. So I should say I did not assign those sources earlier, but the gauge field is the source for the current, and the metric, let's say G alpha beta, is the source for the energy momentum tensor. So that's how they are assigned. And we can recall Onsarger relations. Now, what is an Onsarger relation? So this type of two-point function where you have T first and then J, that should be related to the flipped version where you have the JT retarded Green's function, and then you have out here you have the two eigenvalues of these two operators under time reversal, or parity. Like it depends on how exactly your conventions work for the Onsarger relations. But yeah, let's call it time reversal eigenvalue of T and J here. That goes here. It could be plus or minus one. Plus or minus one. That's what the values that these still take, and that's the Onsarger relations. And those give us restrictions we see that on these hydrodynamic two-point functions. And just imagine these two-point functions were derived from these on the previous page from these energy momentum tensor expressions, for example. So you will see that there will be terms that come out here that contain, for example, if we vary this T mu nu with respect to A alpha, the gauge potential, then you can rewrite the magnetic field in terms of that gauge potential, and this term will contribute to this two-point function, for example. and so will many of them. Okay, so you get an expression for the 2-point functions. That's the upshot here. And you can restrict them by symmetry, by the symmetry relation, Onsarger relation. That gives you restrictions on the transport coefficients themselves. And then you can generate or construct an equilibrium generating functional. So that's what we normally do in effective field theory and particle physics, for example. We construct a generating functional from which we can calculate everything. So it will schematically have to form that the energy momentum tensor and this multiplies the source, its source, and the current multiplies its source, the gauge field. And so this is the form of that generating functional in equilibrium, hence the subscripts EQ. And this WS can be written out, parametrized in the form that there is some function P of the hydrodynamic variables, that's the temperature, chemical potential, and the magnetic field in this case. And these are the only variables because this needs to be a scalar. So there's only these quantities are 0th order in derivative scalars. So this is the leading term. If you want no derivatives, so 0th order derivatives, this also includes if you include gradients, then this also includes gradient corrections. And explicitly, you can construct other tensor structures which are scalars. So this whole thing needs to be a scalar, right? So you can construct these SNs. And remember, one of these SNs we saw on the previous slide showing up in the constitutive equation. It was a term. Oops! It was a term where this S2 was multiplying some M2, some susceptibility, as I called it. And this S2, that's where it appears here, right? So this appears in the generating functional, and it has this form. It's a anti-symmetrized contraction of the fluid velocity with a magnetic field and then the gradient of a magnetic field. So I like to call this a magnetic vorticity because it resembles the form of a vorticity if you have the fluid velocity, if you had a U here and a U there. Okay, so let me move forward. So from this procedure, we can get two types of Kubo relations. So remember the Kubo relations now, where we can relate the 2-point function on one side to the transport coefficient on the other side. So very simple example would be if you had, say, a 2-point function G retarded that goes like omega squared sigma, and then you have omega plus I k squared d, and you're asking the question like, how do I calculate this this sigma here from such a 2-point function? Then you see that you probably could divide by this omega squared first. So you divide both sides by that omega squared, and then choose a reasonable way of taking limits in order to get rid of the omega term and end up with the sigma term. So let me just try that. So let's take GR divided by, and I run into this writing here, but okay. So I get something like sigma divided by omega plus ik squared d. And so now if I were to set, let's say, k to 0, then this term disappears. And then I could multiply by omega, and this quantity would then tell me what sigma is. That's not the usual way to go about this. Alternatively, you could say in the beginning, you find different ways of ordering this limit. So the point that I'm trying to make is the order of limits matters that you apply to this Green's function. If you first send omega to 0 and then k to 0 as you as the retarded Green's functions depend on omega and k, or if you flip this ordering. So that matters. And this is what this slide is supposed to express. So depending on that ordering, you end up with two different types of transport coefficients. And so that's the classification that I allude to here. There's the thermodynamic transport coefficients, which are of the form correlation function. You first set the frequency to 0, and then in the end, after that you take the momentum to 0. So that both limits are implied, like that last limit is implied here. So if you do that in that ordering, then you get a Kubo relation for this M2 coefficient, which is one of the new ones. It's a perpendicular magnetic vorticity susceptibility. I'll highlight what that means in a second. It's a thermodynamic transport coefficient because it needs no dynamics. So that's the idea. That's why it's thermodynamic and not hydrodynamic. So I will distinguish these guys. These you could also think of as susceptibilities. There's no time dependence. They can be calculated in equilibrium. So 0 frequency means there's no time dependence. There are 3 new ones and of this type, and then further other ones that I will mention later. So I will not discuss this part here of the slide. So instead, I will contrast these thermodynamic transport coefficients from the hydrodynamic ones. The hydrodynamic ones, there we turn around that limit and say we calculate only 0 momentum 2-point functions, and then in the end take the limit of the frequency going to 0. So that is how you get then the conductivity. And this is again a familiar example that you might have seen, where you just calculate the standard charge conductivity from the 2-point function of a current. And so this is in that sense a boring example because this has been known already. But then the idea for us is we want to apply these methods and find something new in the strong magnetic field. And here is one of the new quantities, as I promised. Here's an interpretation of that M2 coefficient, which we call perpendicular magnetic vorticity susceptibility. It is showing up in a system where you have, for example, a gradient of the magnetic field in the y direction. So the x direction magnetic field has a gradient in y. And you have a magnetic field in the z direction. So just together, of course, these you can write these as one magnetic field vector. It has this property. And in such a configuration, such a magnetic field configuration, you have a response of the system, which is due to the magnetic vorticity. So I already mentioned what I call this magnetic vorticity. Here's the full definition. I call it omega b with a 1 Lorentz index, so it's a vector. Actually, it's a pseudo vector, and you have this particular form of it, definition of it, and in this example, it looks like this. It's a dx by minus dy bx. So it's a vorticity in the magnetic field. So it's eddies in the magnetic field, and so as a response to these eddies, you have a shift in the energy, in the equilibrium energy, and the magnetic field in the pressure. So the magnetic field causes a change in your thermodynamic quantities, energy, density, and pressure, and it's proportional to this coefficient M2. And then you dot the magnetic field into this magnetic vorticity. So this is the example written out. So what this is you can think of this as in other examples where you have a fluid which is charged and you have a magnetic field acting on that fluid. Then the pressure in that fluid will change, because what will happen to your particles that are moving, they will have a Lorentz force acting on them because they're charge carriers that are moving. And so the magnetic field will act on them and create a Lorentz force. So that will create a force on that fluid surface that is moving. And that surface, of charged particles in the fluid that is moving. And so this creates a pressure, right? And a contribution to the pressure because it's a force on the surface. So that is the kind of effect that we're talking about here. And in this case, it's not just that the magnetic field is going along one direction, but we're talking about eddies of vortices of magnetic field, but it's a similar effect. It's shifting the energy density and pressure. So that's one effect. Let me talk about, as far as I look at the time, I might have, is it true, 5 minutes? Is that?
Yes.
Okay, so I will finish up in 5 minutes. So the hydrodynamics of the C10, this shear-induced Hall conductivity, what does it look like? So in some sort of experimental setup, we might imagine a pipe or something where you have a shear in the fluid flow in the ZY plane, or maybe the flow between two surfaces. So this might go down on the other side, like some Piezoe surface or so, like some sort of flow that has a gradient. That's the point. It has a gradient, a shear in the YZ plane. So that's the fluid flow. The fluid velocity has this form indicated by the arrows, and that creates a charge response. So this simple shear creates a charge response perpendicular to this plane on which the shear is, by this shear-induced Hall conductivity effect. And that happens when you have just the magnetic field needs to be there. It's not shown here, but it needs to be present for this effect to happen. And so this effect is measured by this coefficient C10. And here's the shear, dy uz plus dz uy. That's exactly describing this shear in this plane. And we also give a Kubo relation for this coefficient C10. It's actually a 2-point function of the energy momentum tensor with itself. And this is a novel Hall response. It's a new type of Hall response, which remarkably is sourced or induced by something that has nothing to do with charge. It's just the shear, right? The shear, it's a geometric shear in the fluid. Between different fluid surfaces, you have a shear, and that's creating a current of charges in the perpendicular direction. And that's an interesting interplay between shear and charge caused by the presence of the strong magnetic field. So this is also the one where I have an experimental setup in mind that we can chat about if you're interested. This is work in progress, so I don't have slides on that for now, but we can talk about it. There are 3 more novel coefficients which I find interesting. I should also mention this is non-dissipative. So that is probably why I find this most interesting. So this is it's a Hall response, and it's a charge current, and it doesn't feel any resistance. It doesn't dissipate any energy. It doesn't generate any entropy. So in this sense, it's like a superconducting current. So this is why this effect is so cool and so interesting to me. Almost
I have a question here.
Yeah, please.
I mean, the question boils down that I don't understand hydrodynamics, but so let me phrase it in this way. Hydrodynamics deals with conserved quantities. Mm-hmm. So the fact that here is non-dissipative current is an assumption or is it a result?
That's a result. Yeah, that's a result. So you get this as an outcome from the entropy current argument. So what I mentioned here in this slide here, point 3, that's exactly where you can find that this this particular effect that I just showed, this C10 term, does not contribute to the entropy current. So it does not generate any entropy, and it is as such not dissipative.
Okay, so then I have a second question here. Since I have a non-dissipative current, and if I will standard Kubo formula way calculate current correlation function, it will have a delta function 0 frequency, something that we will call Drude weight, because this is this non-dissipative part which under the time evolution is just not dissipating. But then I'm absolutely confused. in the order of limits when we take Kubo formulas, because then this becomes important.
So let me try to understand. So when we talk about the
if I calculate current correlation function, I'll get zero frequency response, which is non-dissipative current. But then the limits here are important to take first momentum to infinity and then take time to infinity, not the opposite around, because this is really Q0 property. Well, the K0 property.
I have to actually look at something. So this is C10. This is in the lower table here, and this is as a effect that appears that needs the dynamics. So what the order of limits that we're performing here is you set the momentum to 0 first. And then the frequency. So in that sense, it's on the same footing as the Hall viscosity or the Hall conductivity.
Yeah.
And maybe that gives an answer to your question.
No, yes.
Or maybe that's what you said already. I'm not sure.
Yeah. I mean, exactly. That's my point. I mean, so if you could express this current in the language of second quantization, we can numerically calculate it just as a current correlation, and this will be just Drude weight at 0 frequency.
No, but this is not current correlator. This current.
No, I agree. But to claim it that it's non-dissipative, the correlation of this current should have 0 frequency delta function. In other way, it will be just dissipative.
No, that's not correct. I mean, if you compute the correlation function for the whole conductivity that you need to compute, is just Jx, Jy. I mean, in that case, you don't have you don't have like the divergence of the delta function. It's not there. The delta function appears in the longitudinal conductivity, which is a Jx, Jx 2-point function.
Yeah.
And then here he's computing, can you go back to the Kubo formula, Matthias? I think it was a stress correlation function. So I guess that correlation function should not have a Dirac delta.
Yeah, I think this is a bit intertwined. Yeah, so where was it? This was the slide. So yeah, it's a stress correlator here. So I mean, the reason why this shows up in the stress correlator is that this is born out of a shear of the fluid.
I mean,
we tried to find a 2-point function where this is just a current correlator, but that doesn't exist. We didn't find any Kubo relation where we could relate this to JJ correlators.
Okay.
So I think the problem is that our intuition about is normally for current correlators to either give a charge conductivity, or if you think of Jx, Jy as I think Piotr and Fran were mentioning, then you get the Hall conductivity. But this is an entirely different beast, because it shows up either in the TT correlator or in some sort of mixed TJ correlator. So I think it's a good question. So how would I think of this in terms of some sort of standard approach, Drude or so? Like I don't know.
Yeah, thanks.
Yeah, there's more transport coefficients, but let me just in the interest of time not talk about them. Let me also skip these results. They are for weak fields. What are the eigenmodes? So that's not central. So I will focus on like showing you that in the last minute that I don't have the holographic model that where we calculate these transport coefficients that we just looked at. So we can calculate these values for this n=4 superang-Mills theory, for which we have a holographic dual. And so the holographic dual consists of a action that's creating the n=4 superang-Mills theory. So this is dual to n=4 superang-Mills theory, this gravity action. It's basically an Einstein-Hilbert action with the Ricci scalar and the cosmological constant, some Maxwell term and some Chern-Simons term. And this Chern-Simons term encodes the anomaly coefficient. So this gamma over 6, this encodes the chiral anomaly in the dual n=4 superang-Mills theory. So we use this merely to show that what I've shown you previously, what we constructed, that these 2-point functions can really give rise to reasonable transport coefficients using 2-point functions that are calculated in this system here, which happens to be charged magnetic leg branes that we need to use, and then we calculate fluctuations around them. You can ask me more details if you're interested in this, and from that we get 2-point functions of n=4 superang-Mills in a charged state with a strong magnetic field, so just exactly what we wanted. And so then we can use the Kubo relations that I've shown you previously and to calculate these transport coefficients. So one is the M2 that we saw before, that's the susceptibility that we talked about. And here's the chemical potential in relation to the temperature. Here's the M2 on the vertical axis. And we see curves for different magnetic fields. So we start with the lowest magnetic field, that's the red curve, and go to the purple, that's the highest magnetic field. We relate everything to the temperature because that's the scale that rules everything. And so we see that there's just little change when we increase the magnetic field here in this. There's some considerable change. There's some change, but not huge. What's interesting is this effect, this perpendicular magnetic vorticity susceptibility needs the chemical potential to be non-zero, right? Because if it's zero, it vanishes. That's something we see here. So it's truly a non-zero effect. So that was what we wanted to see. It can be calculated in this model, and we calculated it from the Kubo relation we had derived hydrodynamically. Then the second point, the second transport coefficient that I want to show you out of this collection is the shear-induced Hall conductivity C10, which we just discussed, and normalized to the temperature again. This magnetic field is also normalized to the temperature. So this is B divided by T squared. That's what B tilde is. So you see that this effect needs both the magnetic field to be non-zero, because if it's zero, then you see that effect is zero, the C10 is zero. And it needs the charge, the chemical potential to be non-zero, because if that is zero, then this effect is zero for all magnetic fields. So this is the C10 that we just discussed. It needs both a magnetic field and the chemical potential in order to have this coefficient C10 non-zero, this shear-induced Hall conductivity. And we check that also in our holographic model. We can obviously check all the quantities all the relations that we talked about before, like Onsarger relations for the 2-point functions. They are all satisfied, and that's why we believe that this whole description in the hydrodynamic regime is that we constructed is reasonable and works. So this is a test that it passed. I will not have time to tell you about this, so I will just mention that this particular system that I just looked at, the holographic model, has a quantum critical point. So it has at zero temperature, has at a certain critical magnetic field, has a quantum critical point, and one can study the physics near that. And it would be interesting to use our model and study it, study the chiral hydro as we go closer to the quantum critical point, see what happens there. Take that just as a remark, and so I will not have time to talk about these parts. So I'll summarize. We constructed 3+1 dimensional hydrodynamics for charged fluids and strong magnetic fields, and there's the counting varies depending on what you call new, but 8 is what I count novel transport coefficients at leading and subleading order in the hydrodynamic expansion. These are as important as shear viscosity and charge conductivity because they show up at that first order in gradients. So same order of magnitude as charge conductivity and shear viscosity. And we've shown that they are sizable. Just if you go back to this here, they are sizable. These are on the order of where also shear viscosity and the other quantities are. So these are not negligible. They are not. There's no separation of scales or anything, at least in the model that we calculated. So these are effects that we have shown in this model to be present and to be relevant. And so an interesting point, well, we have calculated Kubo relations for actually 25 transport coefficients, and I mentioned quantum criticality as an interesting prospect to go close to a quantum critical point and try to describe the dynamics of the hydrodynamics of a fluid there. So just to flash this at you, you saw this before, here are all the coefficients that we calculated, and for each one there's a Kubo relation in the paper, which is published now, and the link will be on these slides. I'll send you the slides, the updated slides. Okay, that's it. As I'll say, if you the outlook, I'll just say thanks to my collaborators and thanks to you for your comments and for patiently listening.
Thanks a lot, Matthias. It has been a very nice talk. So I guess we have time for some questions. So
maybe I leave the outlook here.
So if anybody has questions, please unmute them.
So can I?
Sure.
First, I need to apologize for my ignorance because my background is completely somewhere in microscopic theories. But I have a couple of questions concerning your talk. So I'm sorry, maybe they are very naive. But the first one and the very general one is, where does quantum mechanics enter this picture?
Basically, when I write everything as one-point functions. So when I say that, when I talk about these one-point functions, that the currents that I construct in these constitutive equations, the conserved currents, when I say that they are one-point functions, that's where I say that I'm talking about thermodynamic average, but also quantum mechanical average that I'm talking about here.
So there is Planck's constant somewhere in the theory or not? Is there a quantity which you can go to large values to make the theory more classical or not?
Well, this is difficult to disentangle because hydrodynamics is a macroscopic theory by definition. So in hindsight, disentangling the quantum effects from the non-quantum effects is a little difficult. But okay, one thing that I can say is, and maybe that's the thing that triggered your question. So let me try to say that here. So maybe this slide is better. One thing that was crucial for us was that this conservation equation of the current that we were talking about, the current one-point function, is actually now not zero. It's not conserved anymore, but there's a quantum anomaly. There's C E dot B. And this is the chiral anomaly that leads to this term. So in quantum field theory, you would calculate a triangle diagram. Piotr and Fran know this very well, and probably many of you as well. So, but the point here is the step from this conservation equation to this non-conservation equation, that is quantum mechanics, right? Because this is a quantum anomaly. So in that sense, this coefficient C here contains what you're looking for. It's kind of a measure for the quantumness of the system.
Okay. So you mentioned that the system is not dissipative, but then does this effective theory describe superconducting system or not? Because in superconductivity, you don't have charge conservation. U1 symmetry is broken.
So it's not superconducting. So that would be a whole different beast. So this is all normal conducting, and there are just some dissipationless effects that emerge because you have a strong magnetic field and an anomaly together.
So there is no Meissner effect.
No, because this type of symmetry breaking is not occurring in this system. That's not the reason. So the way that what you're describing, the symmetry breaking in a superfluid or superconductor, that symmetry breaking of that U1 symmetry is giving rise to this dissipation, this transport. But that's not the mechanism that leads to the dissipationless transport in this setup.
Can I maybe just like make a comment as a kind of like translator, as a intervene as a translator, maybe to use a language that I don't know if will be more clear for Maciej. So just imagine that you have like so we know that in like Weyl semimetals, the number of Weyl cones is always even. But just imagine that you have a Weyl semimetal with a single Weyl cone. There is only one Weyl cone. And for some particular reason, I mean, interactions are very strong and the system is very clean such that momentum is conserved. Then in that system, electrons are behaving like hydrodynamically, as we already know that certain electronic systems can like behave. Now you take that system and you apply a magnetic field, which is not a quantizing magnetic field. That's the reason Matthias is working in a regime in which magnetic field is much smaller than the temperature square. So that's not a quantizing magnetic field. And then you ask, okay, what happens with that hydrodynamic system? So this like the properties of that electron system that behave hydrodynamically when I have a magnetic field applied. And so this construction on everything he's talking about is just like in a situation, imagine a situation like that one. I don't know if that more or less gives you like a more sort of like intuitive picture of what's going on. And then when he's when he's writing constitutive relations, those constitutive relations are precisely expectation values on a thermal state using linear response of the quantum operators of the electrons. I mean, you define your quantum charge operator or stress operator, and you take the quantum expectation value, but you do that on a thermal state.
Okay, thank you for the explanation. But you mentioned some real system, so it can be applied to some concrete physical systems.
Yeah, you mentioned so you're referring to the
there was some formula. You just flash this slide. Probably the next slide. Oh yeah, here the last point. Iridium oxide.
That is the material I believe that they look at and propose in this Nature article. So the idea was that these. So the idea is twofold. So the Weyl semimetals, some of these effects are not new that I'm describing. We already we refined effects that have been found before. So let me just say that as an example. So maybe that's helpful. So here in these Weyl semimetals, something has been measured, and maybe there's a little bit of controversy, but this chiral magnetic effect. So you have a current, a charge current, a vector current. Let me label that JV. And it's proportional to the chemical potential, the axial chemical potential, so μA, times the magnetic field. So this is an effect that is also occurring in our system or in our construction, but this is something that has been already measured in these Weyl semimetals. And why am I mentioning this? Well, because this effect is so there's another factor here that's C, And so what this effect needs to be showing up in these metals and to be measurable is the anomaly. That's the C that's coming from the chiral anomaly. So some quantum physics that went into our discussion, our construction, and it needs a magnetic field. So these two are also the main ingredients for the effects that I described in my construction. And so this gives me hope that since this type of effect has been measured in these Weyl semimetals, that these Weyl semimetals also are a good ground for these other hydrodynamic effects that I mentioned.
But I guess it's like fair to say that it's a little bit of a sales pitch. So like what people measure usually is this like negative magnetoresistance, and there are like some controversies. So as Fran was saying that, you know, in real materials, the Weyl cones always come in pairs. So usually it's not possible to measure these like non-dissipative currents. One has to include some like dissipation and then, you know, see how this dissipation influences that. And it's not so like clear, like in the experiment, how to like disentangle everything. So I think it's a long way still to like say, okay, we can measure this or that like precisely.
Yeah, it depends. Like last week I talked to Dima Katseev and he was of course saying that it has been measured, but I agree with you, Piotr, that
no, I think regarding chiral-magnetic effect, there is no, I mean, some people may argue that it's controversial, but I think it's more or less generically accepted that has been measured. But the point is that the way you have to measure, you have to find out a proper way to measure it, because there is an ingredient that you didn't emphasize in this formula, which is the axial chemical potential, and that's something that you don't have in the material, that you have to generate. And then there is like an important subtlety on how do you generate that dynamically. So, I mean, I have like many questions, but I would like to see if if someone else in the audience has a question, and then we can just switch to if there are no questions, then we can switch to the informal part, and then so if someone has a question.
Maybe I can just finish the comment why I think this is
okay, sorry.
The reason why semimetals might be interesting, and that's because of the existence of this quantum critical point there. So that is the other point why I think it might be interesting to push our description to its limits and then understand, use this method to derive maybe some framework like we did, but for like chiral quantum hydrodynamics or whatever you want to call that. So the transport phenomena near the critical point. So, and we can do that in tandem, both like with the holographic model, because we have a holographic model which models exactly this type of thing, and we have the hydrodynamic description, or we can construct one that is also valid here. That's the idea.
Okay, thank you.
So, any other question? Okay, if not, then we thanks Matthias again, and we conclude like the formal part of the seminar. I will stop recording, and